All right, hello POE students. I'm going to go over these notes, Heat Notes Part 2 with you kind of briefly here. Just cover the main points on these. Remember, you have this as an assignment to turn in your notes that you take in your notebook, everything that's in yellow, answering these questions, numbers 1 through 7, and then submit your answers to the assignment. So the first question here is what controls how fast heat moves through a material, and you've got the kind of the material is important. In other words, is it an insulating type of material or is it a conductor? Conductors generally are metals, and the heat moves fastest through a metal than it does, of course, through an insulator. Insulators slow the movement of heat. Things like styrofoam, air, plastics are good insulators. The temperature difference is the difference between the two areas, or the difference between the two materials. So really cold objects can cool your hand off faster than a warm object. Okay, the difference in temperature would just be subtracting the lower from the higher. So if you were talking about the difference in temperature outside a -20 to the temperature inside 70, it'd be 70 minus a -20 would be a 90-degree temperature difference. Okay, the area, of course, is the length times the width, and more heat can move through a larger area than through a smaller area. It's like if you have a big house, it takes more power to keep the temperature inside at a warm temperature compared to if it have a smaller house, because the walls are smaller, exposed to the outside, and just is less area. So the heat won't move through a smaller area compared to a bigger one. Puffy jackets are warm. You have lots of, and this deals exactly with what we were just talking about, through a larger area. Okay, so you've got all these materials like down feathers or some type of an insulating material, and it's usually puffy, and it creates airspace in there, which is insulating, and then you have lots of area for the heat that heat would have to get through in order to get to the outside. Which bench would you want to sit on, and why? Outside, if it's -20 degrees outside, either bench is going to be sitting there on the side of the street, and it's going to be -20 degrees because it's the same temperature as the environment around the bench. So whether it's a wood bench or some type of a metal bench, it's sitting there at 20 degrees, -20 degrees. But you guys know that it's a lot colder to sit on a metal bench than it is on a wood bench, and the reason is because heat travels from a hotter to a colder. Your heat from your body is going to be traveling into the conductor, which is the metal. The metal bench is going to conduct your heat from your body a lot faster than the wood bench. So what you get is the cold replacing the warmth of your body that's leaving, and you're feeling that cold. Okay, and this is the same thing. If we were at school, we'd be doing this, feeling a metal plate and a piece of insulation. Okay, R value is the thermal resistance of a material. So the measure of a material's ability to resist. So when you think of R value, we're thinking of resisting the flow of heat. So a high R value is going to resist flow of heat. A low R value is going to resist the flow of heat at a lesser degree. So some R values are given per inch. So you'll have to do some calculations. I'll talk about that in a minute. In order to find the R value of something made up of more than one layer, we add up the R values of each of the components. So your total R value is the R value of 1 plus the R value of 2, however many layers that we have. So this next one here, question number 3, what are the R values? How do you find the total R value? Okay, the R value, again, we just looked at this. R value is thermal resistance, okay, the ability to resist flow. Okay, and this is just a chart. It's called an R value chart. And we've got different kinds of material here on the left side: drywall, different thicknesses, particle board, 1/2 inch and 3/4 fiber board, extruded polystyrene, 1 inch, 1.5 inch. And then here on the right side, we have the values for each of these different construction materials. So we have R value of the drywall here at 0.45 all the way down to the last one here. The foil face poly at 1 inch is 7.2 R values. And in the lower right hand corner, we have R values. Let me change and get the ink here going. R values right here. Some of these are all listed, and they give R values per inch. So however many inches you have to multiply the number of inches times the R value. So if you have extruded polystyrene, this last one here, however many inches you have, you would multiply it by 4. So you have 1 inch, your R value is 4, but if you have 2 inches, you say 2 times 4 gives you an R value of 8. Okay, so that's we will use that quite a bit, especially for fiberglass batting. So what is the R value of the wall? This is another one of your questions. So in this wall, we have on the left-hand side what's called the R value at the cavity of the wall. Okay, and each one of these here, you've got, first one is 0.56. Okay, 0.56 is the R value of this gray part right here. The arrow's pointing to the gray part. 5/8 inch drywall. This is like if you were looking, this is what we call the cross section of a wall. Like if you're looking down the end of a wall, this is the 5/8 inch drywall would be the inside of the wall, and then the red brick way on the outside would be the outside of the wall. So you're looking at what's going on inside the wall. Okay. Next to that, you've got this 6 inches of fiberglass batting, and it's the pink part here in the middle. So for this one, we've got the value is 3.142. That comes from right here, okay, right here on the chart. 3.142 is for fiberglass batting, okay, but it's times 6. Remember, for fiberglass, we multiply 6 inches times the value per inch. Okay, so we're multiplying 6 times 3.142 gives us a total of 18.85. The next layer is the blue layer here in the middle. This one here, the blue layer is this foil face poly, and it's 1 inch. It has a value of 7.20. That's this right here. So we've accounted for the drywall, we've accounted for the fiberglass. Now we're accounting for the 1 inch foil poly. And then the next is this white space right here in the middle. That white space is airspace, and it has a value as well, 0.17. And then the last thing is this last part, the red part out here, is a brick, and we've got the value for brick right here is 0.8. In order to get the total R value for this, we add them all up, and when we add 0.56 plus 18.85 plus 7.2 plus 0.17 plus 0.8, we get 27.58. That's the R value at the wall cavity. The difference between the wall cavity and what's called the R value at the stud location, okay, this over here on the right hand side says what is the R value at the stud location. The difference is this thing right here. Okay, that tan color thing is a 2x6 piece of wood. It's called a stud. Okay, and that R value at the stud is 6.88. Okay, now remember up here Where we had the fiberglass, we had the R value is 18.85. But down here, where the stud location is, there is no insulation. It's just made of wood. It's the wood structure for the wall. Okay, and these, the 2x6 pieces of wood, the 2x6 studs, are every 16 inches in the wall. And then in between those studs is the fiberglass. So in order to calculate the total R value, in other words, through the stud or through this area right here, from here to here, okay, from inside to outside, we still have the 0.56 for the 5/8" drywall. Now we have 6.88, okay, for this right here for the stud. We have 7.2 right there for the foil, this the blue. We have 0.17 for the airspace, and we have 0.8 for the red brick. You add them all up, and we get the R value at the stud location is 15.6. Quite a difference between the R value, okay, between these two. Okay, 27.58 is much better than 15.6, and the reason is because this area right here, okay, which in the cavity is filled with fiberglass batting, which is a good insulator compared to the wood. So that's the R value of the cavity where the insulation is, for the fiberglass insulation is, compared to the R value at the stud location. The differences between the roofs here, there's a number of things that would be different, but you're looking at the snow on the top, and you can see that in some areas the snow is melted off, and some areas the snow is still on the roof. Okay, it would have to do with the insulating value of what's underneath the roof. Okay, if there's not good insulation, remember, heat travels through the material, and if there's enough heat that travels through the material, the snow is going to melt away. Where there's not good insulation, okay, because if it's not good insulation, the heat is being conducted and it's going to escaping from the house. Okay, where there's snow on the roof, you can see areas where there's snow on the roof, be better insulation underneath it, and the heat can't get through, and it's not melting the snow. I'm going to just go over very briefly the formulas that we're going to be using to calculate thermal conduction. This is what we call our power equation. Okay, I'm not going to go over the examples with the math. I'll do some different videos for that. But this is the power equation right here, and you've got what the different letters symbolize over here on the left. So you've got P stands for power, is the watts, the amount of energy, heat energy conducted every second is joules per second. K stands for thermal conductivity, which is how easy does the heat move through a material. The A stands for area in meters squared. The triangle T is actually delta T, is the temperature difference. And then the L stands for thickness. And temperature difference was in degrees Celsius. Thickness is also in meters. So this is a math problem. The formula is power equals the thermal conductivity times the area divided by the change in temperature. Thermal conductivity times area times change in temperature divided by the thickness. Okay, and this is a math problem that is using that formula. It's a word problem that uses that formula to solve for it. And there's a couple of the numbers are given here for you, okay, to show you how to do it. And this is just another problem, and again, I'll do a different video to go over that. But then I also want to show you the formula for actually define heat capacity, and then show you the formula for that as well, because this is the other math formula that we'll be using in this unit. Heat capacity is how much heat it takes to change the temperature of a material. Okay, it depends on the amount of the material and the type of the material. Heat capacity, the symbol is is the letter C, C for capacity. Sometimes you'll hear it'll be called specific heat. Sometimes it'll be called specific heat capacity. Sometimes it'll just be called heat capacity. That means people are talking about the same thing when they're describing it. Okay, how much energy it takes to raise 1 kilogram of a substance 1 degree Celsius. Okay, it's a physical property, which means that it doesn't change no matter how much of that material that you have. The specific heat capacity is the same. And there's a couple examples here. Water is measured in calories per gram per degree Celsius or in joules. So two differences: calories or joules, joules per kilogram degree Celsius or calories per gram degree Celsius. And you can see comparison that if you compare, this is aluminum over here, this is water over here. Water has a quite a bit higher specific heat capacity, okay, than aluminum does, or any metal for that matter. Okay, your formula that we use to calculate how much heat it takes to change something's temperature, this is your formula right here. Here are the symbols. Q stands for the energy, and that would be in joules. M is the mass, that would be in kilograms. This is your specific heat capacity, typically measured in joules per kilogram per degree Celsius, and this is the change in temperature. Heat energy equals mass times specific heat capacity times change in temperature. This is a math problem, and again, I'll make another video to talk about showing you how to do calculations using this formula of calculating the energy transfer. So good luck on this. Ask questions if you have questions. Get in those Google Meets and turn those cameras on. You guys can do this.